Good afternoon, everyone. Welcome and thank you for joining us for the GeoDiv's fourth online lecture for this year. Today's lecture is titled Interrelationships between Engineering Geology and Geotechnical Engineering in Cape Town. The lecture today is actually a recording of a presentation that Mike gave to the City of Cape Town back in May this year. The presentation was in fact really well received, so much so that we asked Mike for his permission to share it with all GeoDiv and SAICE members. So thank you, Mike, for allowing us to share your presentation today. Okay, so although today's lecture is a recorded presentation, Mike is online with us today and will be available for the Q&A session at the end of today's presentation. So hi, Mike, welcome and thank you for joining us. Okay. As always, before we start, just a bit of housekeeping. Today's lecture will run for about an hour, following which we will open up a Q&A session at the end. We will generally allow 15 to 20 minutes for Q&A, depending how time goes. The Q&A session, however, will be open during the entire presentation. So please, if you have questions, please feel free to ask them when and as needed. If we may ask, if there is a slide in particular that your question is referencing to, please include the slide number. As mentioned, we will let the presentation run and we will get to the answers at the end of the presentation. There are CPD points for today's lecture. There will be an attendance register that I will post shortly in the Q&A section. It will be a link to an office form. Please complete it and submit for CPD points. Today, I will also post an evaluation form along with the attendance register. Please, if you can, take 2 or 3 minutes just to complete the form. It really does help us plan for future lectures and other events. Okay, so before we start, I want to give a brief introduction for Mike. Mike has a BSc and MSc in Civil Engineering from 1973 and 1976 respectively from the University of Natal, and a BSc in Geology from the University of Cape Town from 1981. He lectured soil mechanics at UCT for 4 years and has been working as a consultant since 1984. With his background and wealth of experience, he understands both the engineering geology and the geotechnical structure extremely well. In his career, Mike has produced over 1,500 geotechnical reports and designs that are often referenced by other practitioners. Mike is assisting with complex projects and consulting even after retirement. He gladly shares his expertise and novel way of thinking with other engineers. Mike has been a guest lecturer at both the University of Stellenbosch and University of Cape Town and has assisted in adjudicating final year projects and exams. Okay, with that, I think we can start the presentation for today.
Good day, folks. Many people confuse engineering geologists with geotechnical engineers. The two disciplines should, however, be closely integrated for any project, with each informing the other. It is not possible to deal with this interrelationship in any great detail in such a short time, so I have chosen a few aspects and projects to illustrate it with, one of the prime ones being that of weathering. There are many sources of information available to us and should be used before we even visit a site. Let's start with the geological map of the Cape Peninsula. Essentially, what we have on the map is a zone over there, which is underlain entirely by this brown colored material, which is the Malmesbury Group bedrock, comprising predominantly shales and sandstones and greywackies. Intruded into this is the underlying granite, which underlies this entire area here and is colored pink with the Peninsula Pluton, and another Pluton of granite here, the Stellenbosch Pluton. Overlying the granite in this area is a thin layer of shales and sandstones known as the Graafwater Formation, which is generally shown as a very thin blue line on the map, and is what you see on your left-hand side as you travel down Chapman's Peak Drive. Overlying the Graafwater Formation are the peninsular sandstones, Table Mountain Group peninsular sandstones, which are quartzitic sandstone and which we typically associate with the upper part of the face of Table Mountain. They are colored light blue. On these is deposited the sediments in this area, which are either wind-blown mainly or up the coast over there. And around the edge of the mountain, this light yellow color, all the way around there and to a lesser extent here, is colluvial material that has fallen down the mountain and tends to be a sandy, gritty material. In this zone over here, we have more reddish colored and loamy type soils, and that are typically associated with the underlying bedrock that they might be derived from. Here it's mainly the granites, as you might find in the Constantia Neck area, and out here the more loamy stuff overlying the Malmesbury Group rocks. A consequence of all this is that as we move along the coastline here, we will find Malmesbury Group shales and sandstones, and from there on all the way around here we tend to see granite sticking out in the coastline. Here we have some wind-blown sediments of the Fischhoek Valley, where the Fischhoek Fault goes through here, and then we go into the quartzitic sandstones as the sandstones dip below the sea along this coastline. And here we have the underlying granites exposed again along the coastline up to there. And along Muizenberg Beach, we tend to find our nice sandy sediments from over there. A more useful and detailed source of information is the engineering geological map put out by the Department of Geological Survey, where the area is divided into land facets demarcated by, for example, this zone of dots and color, orange color here, and where various codes inside of it refer to different geotechnical properties that are to be found in those areas. Here in the legend that accompanies the map, you have your different codes and the geotechnical properties such as permeability, the aggressiveness of the soil, whether it's subject to wind erosion, whether it's subject to water erosion, whether it's going to settle with being loose sand, shallow water table, collapse potential such as you might find in the Constantia Neck area, active clays ranging from low expansiveness to high expansiveness, how easy it is to excavate, easy to difficult, potential for slope instability, and flood risk. So you can see that it would be useful to hydrologists, for example, in this case, environmentalists relating to erosion, and even to quantity surveyors as they have cost implications indicated down the side. Other very useful documents exist, such as, for example, this publication from Geological Survey at some time in the past, where, you know, before you go and start drilling your boreholes all over the show, you might just want to have a quick look at this and see where the elevation of bedrock is. This gives the coarse outline of different elevations of bedrock below the soil or sediments, ranging, as you can see, from the deepest here and over there, sitting at minus 20 meters, through the intermediate at somewhere between the 0 and 20 meters, and then above sea level, you start getting the yellow and the greens up to greater than 200 meters. Another useful, very useful source of information is the that contained in the 4 engineering geological books of Southern Africa by Tony Brink, which every geotechnical engineer and engineering geologist should have it on his shelf, otherwise he should be shot, and would also be very useful to most environmentalists and other people dealing in natural soils and water and so on. Zooming in a bit, We can see here the contact between the granite and the Malmesbury material, and it even shows the contact beneath the sediments. You can see it going off down over there. In these areas and in these areas wherever rock's exposed, it'll show you the dip and strike of the bedding or the folding, and things like dolerite dikes, which are these little red things going through here, which tend to weather differently to everything else. We have in this zone marked as QT, those gritty sediments, colluvium that's come down from the hillside all the way around here. Here's QT over here as well. And as we go further out here, we get the more organic soils in that area there, and over here as well. Then we have the sort of wind-blown sand sitting in that area there. You can see it, and it even shows you the contact between here, that is all of the fill that was placed in the reclaimed area. You can see QD, and here's all the fill that was placed in the Pardon Island area. So it's very useful to know whether you're dealing with fill or you're dealing with transported or residual soils. Zooming in even a little bit more, you can see that there's a lot more information on these maps than you might expect. For example, here we have the stone quarries that where the stone was taken out of the Malmesbury Group rocks. Over here were the old clay pits that they were used for making the bricks in the days gone by. And I ask you to remember that in terms of deep weathering in the further on this story. Over here, you'll find it all over the map marked borehole positions that have drilled and the depth to either shales or bedrock or granite. In this case, it says Malmesbury Group rock at 5 meters depth over there, Malmesbury Group rock at 8 meters depth over there. So it's very useful if you're planning foundations or drilling investigation, etc. It's even useful for people in environmental or archaeological field. They give you things such as the occurrence of fossils. You can see here 3 sites of fossils and the type of fossils that were found in those particular areas. There's a lot more on this sort of map than you might imagine. Here's your contact between your fill and the residual materials in this big yellow area. Here's also all fill. So very useful indeed. Zooming out again, I forgot to mention that these various springs are shown all around the mountain, where the water that is running underneath the colluvium typically comes to the surface and is of use to the geohydrologist. But more particularly, the contact here between the granite that intruded into the Malmesbury at this point, which was noted in 1836 by Darwin when he came past on the Beagle and contributed to his contributions at the beginning of geology and his treatise on the origin of the species. Zooming in on the contact, you can see it here between the dark blackish colored Malmesbury shales and sandstones exposed by wave action over there and the lighter colored granite on this side. If you stand on that point there, you'll see it very clearly. Looking at the Malmesbury Group rocks to the right of that contact, you can clearly see the strike of the bedding and the isoclinal folding going in that direction. And I know that this area under here is a wave-cut platform, so I can tell immediately that as the sea receded to expose this wave-cut platform, it left behind a surface such as this, which is like the teeth of a saw when you try and walk across it. I don't actually need to go and dig holes all over here to design this building or that building. I know exactly what the bedrock's going to look like when I get to it. Going to the left onto the granites, you can see the jointing running that way and the master joints running this way, which makes this blocky type of rock surface. In this particular area here, this is not a wave cut platform, but a wave cut cliff running along here just below Victoria Drive, which if you stand here you can see very clearly. And but this does tell me that in this zone and in this cliff face, when I'm, for example, digging a hole for that building there, as has been done, the orientation of my jointing and the likely failures of my excavation faces, I know already just by looking at this lot what the rock is going to look like and what the joint orientations are going to be. One tends to think of rock as a stable material, but weathering of the joints and of the rock itself very often leads to geotechnical and slope stability and issues of safety as well. Here's a lump of granite that's decided to detach itself above Nettleton Road somewhere, and in this particular instance we have a core stone which is situated at the top of the old quarry that had this house put inside of it, and the gentleman's bedroom was there and his swimming pool was there, and he woke up one morning and he couldn't open his door because this just happened to be in the way. It had rolled 50 meters down the slope overnight in a rainstorm. It was very lucky it didn't end up landing over here, which might have squashed him in his bed during the night. If I look at Table Mountain on the Apostle side, this little rock here detached itself from there in the Graafwater Formation, very blocky nature and so on, but the weathering, you see a reddish area here where weathering is being undergoing preferential weathering, and this thing went bounce, 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 and ended up here. That's about 50 meters between bounces, and this chappie here is 5 meters from top to bottom. The Table Mountain, the face of that, estimate is receding at around about 1.5 millimeters on average per year, so obviously stuff has got to come down. Here we are in the Graafwater Formation just above Tafelberg Road. Overnight this lot detached itself as weathering took place. The weathering predominantly being a function of the fact that there's a stream running across the top here and it is saturating this area all the time, so you get preferential weathering taking place and final collapse of the rock onto the road. Here, if we look down on Smith's, this is Smithswinkle Bay down here. This is the view site that people stop and look down onto the sea and False Bay. You can see all the little white bollards put here to stop people parking on that side of the road and force them to park in this old quarry site over here, which if you look a little bit more closely, look like this. Very nice place to park. Note the nice big overhang over there and the sort of shear plane or weathering plane existing along that surface there. With further weathering, that whole lot decided to detach itself and came down in a huge, big, humongous pile with some rather detrimental consequences. You can see over here. These people were the only ones at the site at the time. They had got out of their car and were standing on the other side of the road viewing the view, and this lot happened. The dog they left in the car was killed. Weathering. The weathering of a rock to a soil, or the further weathering of a soil
Mm-hmm. Brett, can you hear me? We've lost the sound. Oh no, total fucking. Brett, can you hear me?
Hi, Mike. Sorry, we're just having some issues with the sound at the moment. We are trying to sort that out. To the attendees, I do apologize. We are trying to sort that out from our side. Jacobus, can you maybe go back a slide or two and start playing again?
There's less steep.
Go back to the page on weathering, please.
Okay.
Weathering. The weathering of a rock to a soil, or the further weathering of a soil, from example a sand down to a clay, is a function of a number of different factors. One contributing factor is vegetation, where the roots tend to crack the soil or rock apart, and the chemicals introduced by the vegetation tend to assist the weathering process. The vegetation is in turn a function of the soil, the climate, and the drainage, in other words, the slope. The soil in turn is a function of the rock it came from, whether it be sedimentary, igneous, or metamorphic. The climate, which results in either mechanical or chemical type weathering. The drainage, where, for example, if you've got poor drainage, you might be having clays deposited or formed in place, or otherwise the clays might be being removed to leave an open voided material. Time, obviously more time, the more weathering the process, and hence the more soil. And the transportation of that particular soil by removing it, could be depositing it, could be sorting it by grain size, and the degree of weathering that's going on. Erodibility of the soil at the end of the day is a function of that soil and the vegetation holding it together, the climate, whether it's rainy or wet or dry, suffering wind erosion or water erosion, and the influence of the slope on that. What we have here is the geological map, which is basically types of bedrock, a map of slope, very steep slopes in these areas, the yellow areas, less steep slopes in the green, pretty flat areas in the white, and rainfall, high rainfall as we expect, top of Table Mountain, and lesser rainfall there, very little rainfall down the bottom end over here. Now, an interesting feature of the Cape Peninsula is that if I plot all of the clay pits, the old clay pits where they mine clay, such as the kaolin mines and the brick making pits and so on, they're these green dots, not the triangles, the green dots. And they all fall within a band of contours, that contour and that contour there. Also, if I plot the outcrops of siltcrete, these siltcrete tend to sit either at the top of that band of contours or at the bottom of the band of contours. And between those two siltcretes and where all of these clay pits occur is a band or zone of intense, deep chemical weathering that has taken place in the past. It has been partially or totally eroded away in places now, and this surface, this band around here, is known as the African erosion surface. Now you can appreciate that deep chemical weathering, for example, in this area, would be weathering a sandstone, which would only slightly modify the sandstone to a more friable, softer rock, whereas deep chemical weathering in, for example, this zone around Hart Bay here would be on granite, and it would give you a deeper weathering profile resulting in a kaolinite or kaolinitic type of material, clay, and deep weathering in the Malmesbury's out in this area over here would typically end up in a more elytic clay, not so much deep weathering, but advanced chemical weathering, right? So if you then superimpose all of these diagrams onto this erosion surface where you've got steep slopes, you'd have a different scenario. Whereas if you've got a lot of rain or no rain, let's say in this area here, Camps Bay and the rest of it, you would have a drier profile and a different effect on the weathered material as against, for example, in the Constantia Neck area here, where you would be looking at a much wetter weathering of that old African erosion surface. To explain this African erosion surface, let's go back a bit in time. At around about 18 million years ago, you had this sort of scenario. The sea level was down there after it had been up here and had cut this sort of erosion surface as it receded. We then had a period of very, very hot and wet climate. What that did is it tended to weather this zone here very deeply and advanced in terms of chemical weathering because of the high temperatures and lots of water being present. There were areas, however, where some colluvium, the green colored stuff here, had fallen down and filled this zone before this period of deep and advanced chemical weathering. So you then had a weathering of the colluvium, this colluvial material shown as dotted, and possibly even deeper into the residual material underneath. The rocks would have been either Malmesbury group rocks or the granitic rocks or the Table Mountain sandstone rocks predominantly. Now, the water flow coming out of this higher area here, subsurface water, would flow down and it would bump into this highly weathered zone, which is less permeable, and be forced to the surface. In doing so, it would have silica dissolved in it, which it would precipitate out as it evaporated and left it behind. So you get the silica or your silcretes deposited in that area. Similarly, the water that is flowing through this zone is hitting the underlying bedrock with lower permeability possibly, and being forced to the surface over there, precipitating silica and your silcretes in those zones. And the same would be happening over there and over there. Then moving on to about 2.5 million years ago, the sea has now receded further down there, and you've got some sediments left behind there. So these sediments start being exposed above sea level. Right? If we then move on to, well, this is the same configuration as you saw in the last slide. If we move on to the current situation, 0 megaannums, the sea has eroded a wave-cut platform here in the interim and then receded once again, leaving a little bit of a scarp there. And what we have over here now is recent colluvium that has fallen down and covered over the erosion surface. So in this case, the recent colluvium might be sitting on weathered bedrock, or in this case, the recent colluvium might be sitting on weathered older colluvium or unweathered older colluvium, or even onto weathered bedrock down here at this end of the scale. The subsequent erosion by the sea, by rivers and landslides or whatever could have removed part of this. So it could, for example, have followed that, the ground could now follow this profile, in which case there'd be no sign of the erosion surface left behind here. And we would see recent unweathered colluvium overlying deeply weathered bedrock and unweathered bedrock. Or if it had taken it all the way back here, there would be no sign at all of the erosion surface left. If we went to, for example, having eroded back to here, then you would have recent colluvium overlying weathered older colluvium overlying highly weathered bedrock, grading into unweathered bedrock. Or, you know, over here we could find some siltcrete underneath and go down through weathered colluvium, unweathered colluvium bedrock. Here's an example of very deeply weathered, highly weathered granite with very little colluvium. Here, as we head out towards the west coast, a situation exists where on the African erosion surface we got recently deposited wind-blown sands overlying very deeply weathered Malmesbury group shales, which now take the form of clay silts, the clays being probably predominantly oolitic type clays, the type of stuff they would have used for brick making. Now, if I'm working on the erosion surface, I know that I've got some deeply weathered materials to deal with, but if I take those self-same materials and weather them further, I end up with a slightly different material. So for example, if you take the Malmesbury group transported soils and plot them on a plasticity index chart, you'll end up with them all plotting above, well, not all, but mainly above the activity line. In other words, they're going to give you heave and settlement problems, whereas the residual ones tend to plot all below it. The implication of this would be that I could, if I find clay materials below or towards the bottom of the African erosion surface that have been, can show have been transported, I expect them to behave in a much more active and problematic fashion than the ones on the African erosion surface that are residual. If you plot the same two graphs for the granitic, kaolinitic materials, you'll get pretty much the same picture. As an example, near in Camps Bay, you can see the deeply weathered older colluvium there, which is mainly of granitic origin. In other words, it's come from the granites, and it is deeply weathered to a mixture of clays and silts with occasional weathered cobbles and sandstones and so on in front of it. Here is a ferruginized zone of ferrocrete, as we might call it, which is similar to the siltcretes, and you find it in place of the siltcretes in many places. And here you have the overlying recent unweathered bouldery colluvium. A little bit further along in Camps Bay as well, you can see here a very deeply weathered kaolinitic type of material, which you might expect to be the residual weathered granite below of the African erosion surface. However, one finds the odd highly weathered cobble or sandstone pebble in it, which indicates that it's transported, so hence being a transported portion of granitic erosion surface material, I expect it to be a lot more active than I might find elsewhere. Here's your recent colluvium in the form of a sand sitting on top of it. Another example further down the hill where very much drier scenario prevails. There's the bouldery sand, the recent colluvium. Here's the orange-colored weathered colluvium underneath, which is not that much weathered compared to up, we found further up the slope on the African erosion surface. A consequence of being on the African erosion surface is that the already highly weathered or partially weathered materials, rock or soil that you're encountering, do not take much more in the way of weathering before they lose their cohesion or strength and tend to collapse in road cuttings and slopes in general, particularly if you add a large amount of water in the form of a rainstorm, such as here in the weathered granites, and there's the overlying colluvium. Here's the weathered granite. You on bottom of Chapman's Peak Drive, after a heavy storm, the whole 1 meter or so has sloughed off, taking this Gabion retaining wall with it. There's a previous old slide in the corner that you can see over here. If I go to Simonstown area, here we are, a nice slope, been stable for ages in the weathered granites, but after about 30 or so years of weathering, it's lost a lot of its strength, and you get with a large rainstorm once again a major sloughing off of this weathered material in the form of, there's a scarp face, and this thing was pretty large. It went right over there all the way along here up to there. If we go, for example, to Camps Bay once again, here, this is all weathered colluvium that's just got wet, a broken stormwater pipe or two up the top, doesn't help matters much, and this whole chunk is sloughed off here, laying this nice Gabion wall on its side that was at the bottom of the slope. Going to Boys Drive on the erosion surface, where we have deeply and highly weathered colluvium overlying highly weathered Graafwater Formation bedrock, continued weathering into the cut face resulted in a loss of strength of the exposed material, and coupled with a severe rainstorm, then we had sloughing off of this layer of deeply and completely highly weathered material. You can see the extent of the slip here. Obviously, they had problems here in the past, or experienced problems, expected them, and put in a stone retaining wall over this particular section. What we did in this instance, because we could not excavate at the base for a substantial foundation and had to keep the road open at all times, was quite interesting. Needed to provide some vegetation to hide this horrible slope. We decided to gun out the top portion over there with just some geo-nails. Remember, this is fairly stable material under its current condition, because the poor quality material has already fallen away. So the prime objective now is to stop further weathering in this direction. So you can see here was the loose colluvium on top, and then the ferruginized zone underneath it, and into the residual material there. What we did, however, we couldn't dig down here very much, because and also we couldn't close the road, so we had to do something quite confined. We created a gunite wall against a plank with the anchors already in place, and then backfilled behind it, and later clad the front of it with stone. And there's now a lot of bush growing out of here, bush growing out of occasional planters we stuck in up there. The thing looked like this. Here's the planking at the back, the gunite wall going in the front, a bit of a small foundation just to rest things on. And this is the old stone wall, which is then going to be increased across the face of the gunite to provide cladding. At the back of the planking here are the anchors into the wall, into the slope rather, and they were used actually with nuts and washers to hold the planking in place while the gunite was put on the front of it. We even made it such that we could take the planking out afterwards. And this is the completed thing before the stone cladding is added across the face, and now it's quite well vegetated and reasonably hidden from this horrible stuff up top here as well. Moving on to Simonstown on the erosion surface, a localized problem called in to look at this house. There are lots of cracks here, and obvious conclusion is that this point is settling, and a simple solution would be to underpin it with piles or whatever. However, one needs to keep an open mind and look a little bit further afield with these jobs. A bit further down the slope, there was another building which similar type of cracking, indicating settlement, which would be easily construed as a settlement of the downslope portion of a building founded on the slope. However, if we looked a bit further afield, we will find, or we found, I should say, that this is the house I first showed you. That's the corner that settled. This is the second property that settled on the corner over there. But we then noticed that all of these houses marked around here had similar types of problems and been locally underpinned or treated in a similar localized fashion. If you drive along this road, you will notice that the water main has been patched on a number of occurrences there, and likewise there. And there's also a substantial kink in the pavement at that point. And bottom line is that one has a zone of slowly creeping mobile soil heading downhill when it gets wet enough, encompassing all of these buildings. The guys in the middle, all right, they're sitting on the surfboard. The guys on the edge, however, are sitting with 1 foot on the board and 1 foot of the land and have obvious problems. Bottom line is, always look at the global situation before you narrow yourself down to your particular site that you're involved in. In a similar vein, on the erosion surface in deeply and highly weathered colluvium in Camps Bay, an excavation of some, in a series of steps, 1 step, 2 steps, 3 steps, total height about 15 meters, with a near vertical face over here of around about 5 meters. If you look at the profile, it looks like this. There's the vertical face, and here you can top it, you can see the recent colluvium, which is loose boulders and sand and stuff, and then it becomes this weathered, quite dense colluvium, grading downwards into very highly weathered colluvium, almost in the form of a clay without any cobbles and sandstone boulders or anything like that in it. Note the house next door. Now the house next door, but one, beyond the house I showed you just now, if you looked inside, these are the sort of cracks that you were seeing. Obviously this side was going down, but note this other crack outside the window here. And if we go and have a closer look at that crack, that's what you see. Now that thing hasn't arrived in the recent time. It's been there for quite some time, indicating that settlement of this side of the wall has been going on for quite some time compared to that side of the wall. If I go down into the house I showed you a picture of just now on the other side, it, in its garage, has a crack that looks like that, indicating this top portion of the house and all of the house above it is heading in that direction over there. At the front of the house, this is the scenario that greeted us one morning. Here's the crack in the garage. You can just see it over there. This whole top portion of the house is moving this way. This point here has moved about 300 millimeters relative to that point over there. this whole side wall is moving forwards, and you can see how it's pushing up this bulge of soil and in front of it and over here. A panoramic view of the same thing. Here's the bottom retaining wall that they had got as far as putting partially in place. There's the next step, and there's another retaining wall at the top. Note that house at the top, it's the one with the swimming pool. There's another one with the swimming pool in front of it. The house with the crack in the root in it that I showed you just now was this one over here, and this is the one with the huge cracks in the garage. You can also note a bulge in front of this wall here, as this wall is being pushed forward and forcing up a toe in front of the retaining wall. Here we have two sections through the area. This is the one through the house with the garage. The garage was sitting over here. The original ground line many years ago would have been there. The ground line before this excavation was undertaken followed there's the back of the house running down the garage area over here. We also know from these old stone retaining walls over there that water was coming out of the ground there, and you could also see water against the back face of the garage wall over there. So it's quite easy to put in a water table line on this thing. We've got cracks going down there, vertical scarp face, and we know the front's being pushed up around about here somewhere. So we've got a top and a bottom for the slip circle. On the one where the retaining walls are partially completed, we've got these deep vertical scarp face cracks at the top. We've got water coming out of that slope over there, and we had water coming out of the slope over here. The natural ground line was originally like that. We dumped soil back up to here to keep this in place while we worked our way down, putting anchors through these existing retaining walls. Those encountered water at these various points over here, so we could good idea of the water table. They also encountered clay at that point and that point and that point, and we also knew where the clay was on this excavation, on that excavation, and they picked up water there, and there, which tended to indicate the localized positions of the slip circle. The monitoring is these little arrows here, in the direction and magnitude shown according to scale here. Now the relevance of those is that if you take any one of them, like that one over there, the movement of the soil in that zone must be parallel to that thing. So you can actually get a line of parallelism of the slip circle in relation to your movement vectors. So that one's going that way, so that's pretty so much the same. That one's going that way, that's pretty much the same. Here, that should be pretty much parallel. So having a start point and an end point and the parallel lines, I get a very good picture of my slip circle that would almost be impossible to get by just drilling boreholes and trying to find a shear plane. So what I'm trying to say is use the evidence available to you rather than just blindly going ahead and plugging needles into a haystack to define a problem. Now, this excavation stood quite stable until the rains came and suddenly everything got wet and everything started moving. However, we had previously been called in to look at this house where the owner then subsequently put in a whole lot of big concrete buttresses to hold his front wall up where he had a staircase coming up. When they built this house, they then later came to dig a garage in here and anchor it back. And in the excavation they did to accommodate the garage, everything started moving, and hence the need for the anchors to hold that excavation together. We also found out later that this chap had bought the site very cheaply because the original owner builder on the site had dug a hole and started building it, whereupon the whole lot had started moving. There's also a drainage line that runs right through here and down there. So he had a nice water feature in his lounge with trickling water through coming out on the road down below over here. when we then plotted these scarp cracks up top here in front of this guy's swimming pool, and behind this guy's swimming pool is a swimming pool going down, it became evident that you had an entire zone of creeping soil here that is activated by complete saturation or higher degrees of saturation during the winter period. And once again, it indicates that one should look at the bigger picture before one goes ahead with something like this, or even investigating something like this, as the whole area is basically unstable and not just this localized zone over here. In the same theme of looking further afield first, this is Clifton Beach, and we were to put this building, which is complete in this photo, on the side of that slope over there. Note the rocks in the foreground over here on the beach, and the odd thing about them is that some of them are sandstone and some of them are granite. If we look at, also note this building here, which used to be the old Clifton Hotel, and from the side, that is the building that's constructed there in a series of terraces sort of plastered onto the slope. These are the rocks that we see below, and you can see these various other outcrops of rock, the granite that we looked at on the geological map. Also note this old Clifton Hotel sitting on top here, 4 stories worth over there. Now, however, if we look at that from above, here's Lion's Head, and there is the little outcrop that we are working on. That's the building over there, and that outcrop is a nice solid granite outcrop. This outcrop is a solid granite outcrop. But if we look at the general shape of the area here, you'll note that Lion's Head has this very strange sort of embayment in it over here. This particular area, if you walk through it, has got very little soil cover. It's almost large expanses of exposed granite that you see. And what becomes apparent when you look at it on this sort of scale is that at some stage in the past, this whole chunk of Lion's Head fell away, slid down the hill, shot over here, and ended up forming this little promontory here, which is all landslide debris, the clue being that there's so much sandstone in it as against the granite boulders only. And that is why the Clifton Hotel is there, because that was the very first flat-ish piece of land that they could use for stabling horses in the old track that used to go along the front here. Going back down to the slope below, so now we had indications of the material type already from just having done that little bit of geological investigation and looking at it. The boreholes in this area confirmed it, and we then came up with the idea here that the stuff is fairly competent in terms of compressibility, not so much in terms of its shear strength, but highly variable from boulders through to loose sand and soil between them. And this particular building, we just sort of hung it on the side of the slope simply by friction and holding that against the slope with anchors as against piling it to support it vertically. Note the vertical face at the top over here, and there is the 4-story Clifton Hotel. But Clifton being what it is, everybody wants more space, so they had then decided that the Clifton Hotel, which is this piece up top here, is going to have a basement underneath it. Now remember, there's about a 6 or 8 meter vertical face in front of it with our anchors holding the gunite back, and we had to dig this area out while holding 4 stories up above our head. If we look at what it was like, this is the material we encountered when we started excavating. Clearly all sandstone, massive sandstone boulders, smaller boulders, and loose sand in between. This is landslide debris. Here are the old bases of the old hotel, and this is the sort of exercise that we undertook, where we would be propping an area where there was a column, and it's the first time I've ended up casting bases after the column. So here's a column, and we're going to put this raft in here to support the bottom of the column. And obviously the guys had extreme trust in our propping, and or otherwise the man is oblivious. So with that and all of what I've said before hanging above your head, I have just a couple of thoughts to leave. These include: always work from the macroscopic down through the mesoscopic to the microscopic, your site in other words. Know the geological, pedological, geohydrological and geomorphological setting before venturing to the site. Conduct a literature search, which is more than just a search of the internet, and budget for it. You know how many reports languish on desks and taxpayers' money I've seen spent redoing reports that have already been done more than on one occasion. Ask persons experienced in the area for advice. The geotechnical fraternity are generally fairly free with their information advice. Ensure the topographical survey extends well beyond the boundaries of the site. Number of sites we see where the survey just is taken up to the boundary, and you do a whole design of something and get on site and find there's a great big cliff or a hole in the ground or something like that right adjacent to the site. Use all visual clues around and on the site before planning further investigations. I normally spiral in towards the site, looking at houses and cracks and movements of roads and things before I get to the site. And by the time I get there, I normally know what the problem is and what it's going to be causing it. Avoid using generic investigative briefs, which are intended as a guide in place of relying on suitably experienced professionals to design an investigation. In other words, ask the guys to do an investigation, let them work out how they're going to go do it. Don't tell them exactly how to do it. Adopt a targeted investigative approach that evolves as it proceeds rather than a shotgun approach. Don't have a grid of boreholes and the rest of it all over the show and then find out that they're all missing the one thing that you should be homing in on. Cheapest is never the best, I promise you. Thank you.
Okay, great. So that's it for the presentation. Once again, Mike, thank you for allowing us to share that. To all the attendees, I really do apologize about the sound issue. Mike, I think I might have jinxed something in our 5-minute conversation before we started. Anyway, moving on.
It's inevitable.
Exactly. Okay, Mike, we've had a few questions come through. I would think maybe one or two of them were probably answered as we went through, but let me just start with the ones that came on a bit later. Okay, so we have a question here. When experiencing the slope failure due to weathering or leaching of water through the cracks, how do you know the length of nail anchors to be drilled on soil rock?
Well, I suppose it's, I think in a way I'd answered it with that example of Boys Drive. You know, if all the loose material has literally fallen off, you're back with the original stable slope. So where I often run into a problem is that, you know, a slope that we would accept as being stable in a natural environment is sitting at a factor of safety of 1. Now, suddenly we go and start analyzing it and tell ourselves that we've got to have a factor of safety of 1.5 or 2 or whatever it is. And, you know, then everything becomes, everything you look at needs anchors and stabilization. So I tend to adopt the attitude of that we're back almost to original situation that we would accept quite happily as being stable and in natural conditions. And I just aim at trying to prevent further erosion. So and weathering. So that I don't actually design it as having to check a slip circle or a massive failure, because I won't get a factor of safety in 1.5 unless I put, you know, long unnecessary anchors in. So probably 3 meters would be, you know, the typical length of nail that I'd end up putting in, 3 to 6. Yeah.
Okay. Next question, Mike. With the repaired pipes and structures you mentioned being sensitive to strain, do we have any idea how much cumulative strain has been taking place in the slope and whether we're at residual conditions yet? Was the material approaching residual strength an issue? Can't remember if it was colluvium or residual clay.
Well, look, I mean, if you have a slope or let's say a mobile zone, and it's clearly at a residual angle of friction on the shear plane that where it's taking place. The real issue with something like, you know, if you're looking at a large mobile zone, which is a natural process of eroding and moving towards the sea, then very often it doesn't have a specific shear plane as such. You end up with almost a massive soil that, how can I say, it moves on sort of micro shear planes over the full height of the whole thing. So the top might be moving faster than the bottom, for example. And it's more like a jelly in a way, rather than a specific solid mass moving over a shear plane on the stuff underneath. But if it is a case like the Boys Drive thing or something like that, then the shear plane that it actually finally fails on is pretty much at a residual value. It's certainly lower than what your test results might reveal if you test the soil. Yeah.
Okay, thanks, Mike. Next question. Thank you for a very interesting talk. Engineering geologists and geotechnical engineers should preferably work hand in hand, whilst many companies do not have both of these professionals in-house. What should geotechnical engineers not do, and what should engineering geologists not do?
They should not be on different floors in the same building. They should be in the same floor, because they don't talk to each other enough. That's what they shouldn't be doing, and that's been one of my, you know, the bugbears as far as I'm concerned. I've seen so many engineering geological reports, and they end up on a geotech engineer's desk, and he doesn't even really read it half the time. And vice versa, you've got geotech engineers just putting out generic geotech investigations with a grid of boreholes, as I mentioned, rather than looking or understanding the local geology and then, you know, trying to tailor their designs and their investigations according to it. You know, it's a sort of shotgun approach on that side of things. So I think the bottom line is that as a geotech engineer, I see a severe lack of geological appreciation so that they can fully comprehend what the engineering geologists are putting out. And vice versa, often the engineering geologists are just putting out a report without taking cognizance of what the real engineering question is, you know, in terms of ways of addressing the problem and providing a solution. Yeah.
All right. The next question is quite a mouthful. It's from France, so thank you for that, France.
No, ignore that
one. Sure. Okay. He asks, The Cape Flats area normally consists predominantly sandy, cohesionless soil with some calcrete layers. Often cuts need to be created to install sewer pipes, which shoring dewatering mechanism is the best method to employ in such a profile. Sheet piling requires pre-percussion through calcretes, whilst planking could result in piping and require extensive dewatering. How does one ensure sufficient quantities for these calcrete layers as they aren't present anyway?
Sure. I'm not quite clear of what the real question is, but I mean, if you've got to put a trench through alternating hard and soft layers, and there's a lot of water around, particularly if the water is going to rush in at you from and then cause fretting and collapse of the sand from between these layers into your hole. It is a very difficult thing to dewater. It depends a lot on if you have a clear idea of the layering, where the calcretes are and where they aren't, in which case you could put down your vacuum pipes, some of them to the first layer and then the others below it with a sealed section on the top layer, so that you specifically dewatering that aquifer between different layers of calcrete. If it's a much more mixed up scenario, well, one tends to battle through these things, working your way as you go along.
Okay, Frans, I hope that that answers your question.
We can discuss that one in more detail when we next meet, Frans.
Okay, next question. With the many natural slopes around Cape Town, are you aware of slope movement monitoring taking place along major roads and highways by the City of Cape Town or national provincial government?
I'm not aware of any, and even on I mean, you're talking about monitoring, survey type monitoring where you're measuring the monitoring, but even just visual monitoring, I don't think is taking place. And I mean, it's epitomized by the fact that one of the main causes of failures and damage to roads and infrastructure around Cape Town is the non-maintenance of drainage, because everything is generally got water as one of the root causes, and in particular cut-off drains above cuttings are not maintained at all. So these things actually become dams and tend to cause failures rather than prevent failures. And there's nothing going on in the way of monitoring all this, a little bit now and again, but not on a regular organized basis as far as I'm aware.
Okay. Next question, also quite a long one. Sorry about this, Mike.
No.
Sorry. One often needs to excavate into the residual Malmesbury group. Often shear testing show extremely high cohesion values, which could potentially result in unsafe temporary vertical excavations if water is present. I refer to Settlers Way case study by Brink, where collapse occurred onto workers during construction of the retaining walls. How does one consider relict joints, isolated scenarios based on borehole logs, and what is safe to assume?
Look, the problem with testing those type of soils, as the question alludes to, is that you're not going to take a sample from a borehole core that is falling apart. So you always take the intact material, and that obviously is going to give you a much higher shear strength or cohesion than if you look at the jointing. So I always tend to, I go back to my original sort of beginning of this presentation, from a knowledge of the bedrock before it is weathered, you know what your joint orientations are going to be. And you can then say, well, I've got a joint set which is going to give me a problem even in the weathered state. I'm now looking at a soil. in a certain direction. So that particular face is the face that I would look at and say, look, I'm going to cut that face to the, to parallel the joint set so I don't get failures on it. And your test results are going to be definitely giving you a much higher strength than what you would expect. But the main thing that causes the problem generally is twofold. One, you get a softening of the material due to stress relief afterwards, so it expands and absorbs water. And the second one is that you get hydrostatic pressures in the old joint along the joint planes, causing failure. So I think I'll go back to my thing of saying, experience, use the experienced people to answer these sort of things. And even in this case, it goes right back to, if you read Brink's book, you know about it,
Okay, I've got a question here. The person's name is Lost the Sound, which might be appropriate. Okay, as a non-geotechnical engineer, for my background, where can I get the geological map shown in the start? Maybe I can just scroll up to that.
Geological map shown.
Maybe this was the one shown in the start. Can you see this one, Mike?
Yeah. No, I'm sure. Look, I mean, all of these things are available from, I've forgotten what they call themselves now. They used to be the Department of Geological Survey. And depending on where you are in the country, they've got, an office in Cape Town, an office in Johannesburg, and Durban. So you go along to them and you actually purchase the map from them. I can't give you the exact telephone number offhand, but they're easy enough. So look up, I think it's now the Department of Land Affairs and Mineralogy or something like that. But they are readily available. You can't, I'm not sure whether they've now upgraded to you being able to buy these things online. That might even be a possibility, but they used to be very cheap, but they're now suddenly becoming very expensive.
Okay, next question. The slide which showed the borehole info, clay pits, etc. Is there a resource which continuously updates and adds to this info? I'll try to get down to the slide that showed all the boreholes.
I know what he's alluding to. No, look, the only information you'll get on those is what was available at the time of the production of that map. And I haven't seen any updates on it for ages. And also, one of the things is that there's this incredible lack of collection of data. I mean, as geotech engineers and as geohydrologists, etc., that there are millions and millions of boreholes drilled all over Cape Town, and it's not collated in any single database anywhere. So what I tend to do is I go to the drilling boys and says, have you drilled in this area, or have you drilled in that area? And if they know you well enough, they're probably willing to pass on some information before you even start planning an investigation, if you need to plan an investigation at all.
Okay. Next question. When it comes to the use of rock buttress as a measure for erosion control, which types of soil or site conditions would you avoid? Scenario: road surface at the toe of cut slope with erodible dispersive. Does that make sense, Mike? Sorry.
Not tremendously. I think what he's trying to ask is, if you've got soil and you're trying to prevent it getting eroded by dumping rock against it, what soil would you be able to do it with and against? Look, I mean, the bottom line is that any soil you've got has got a natural angle of repose. And as soon as you're trying to retain it at an angle of repose steeper than that, it's going to try and move through the voids within your rock buttress that you're trying to create. So you've got to put a geofabric or something like that to prevent that migration. Otherwise, it will take place with time, regardless. You know, the rain falls on the soil, it washes the soil, pushes the soil towards the rock, which has got big holes in it. It'll gradually migrate into the rock unless you've got a graded filter in terms of the, you know, like you would do for a dam if you were doing a graded filter design, or otherwise you have to put in a geofabric to stop it. Yeah, that's I suppose all you can do. The bottom, what people don't seem to appreciate is that if you've got soil, you can put it in at its natural angle of repose. So let's say take we normally design a cut slope of 1:1.5 for a, not a cut slope, a fill slope is 1:1.5 for a road embankment. But if you give it time, it will gradually try and erode back to around about 23 degrees. If you look at most slopes that are not currently in nature weathering or being weathered by the process of vegetation growing and then the vegetation sloughing off, they all end up at around about 23, 25 degrees, not 30 degrees.
Okay, another long question here, Mike. Sorry. Victoria Drive Clifton is an interesting environment geotechnically. Original road construction back in the times of Thomas Bain will have involved a significant amount of cut to fill. This leaving an accumulation of recent fill over the original colluvium generally sitting at the angle of repose on the lower slopes. How do you view the stability of undeveloped portions of these slopes under increasing rainfall associated with climate change? Mike, you there? Okay, apologies all. I know there was some load shedding scheduled for Mike's area. I just want to see if I can quickly get him back.
Can you hear me?
Mike, yes, I can hear you now. Sorry about that.
Yes, I seem to have managed to have rejoined you.
Okay, Mike, do you want me to repeat that last question?
Yes, please.
Okay, Victoria Drive Clifton is an interesting environment geotechnically. Original road construction back in the times of Thomas Bain will have involved a significant amount of cut to fill. This leaving an accumulation of recent fill over the original colluvium generally sitting at the angle of repose on the lower slopes. How do you view the stability of undeveloped portions of these slopes under increasing rainfall associated with climate change?
Okay, I mean, well, it depends which part of Victoria Road you're really looking at, but you know, in the areas around Clifton and that, basically cut into rock. There's very little, if any, fill on the downslope side. There's a little bit here and there, but not a lot. But if you carry on Victoria Road, you get into where they've excavated into pretty much weathered granite of the African erosion surface. And there, as over a period of, let's say, 30 years or 40 years, the cut faces have weathered from what would have been a soft rock to essentially a stiff granular type soil. So every time it rains, we get these, you know, small little landslides onto the road. The fill, however, on the downslope side, when they excavated it, it was soft rock. So it was pretty granular type material that in those days they couldn't compact that well anyway, but it was fine. You know, everybody said, well, we've got rock fill underneath these things. But over 30 years, that rock fill has weathered at pretty much the same rate to a clay silt soil, granular soil. And with the consequence that the voids between the lumps of rock and so on are now filling up as it deforms, and you get settlement. So you get ongoing settlement of the fills all along that part of Victoria Road, all along Chapman's Peak, all along Tafelberg Road, and so on, as the in situ weathering process of the fill changes the characteristics of the fill from that of a soft rock to a soil. And particularly if you're adding water and no maintenance of the drainage to the whole equation, you end up with settlement of all these fills.
Okay, thanks for that, Mike. We just have one last question left then for today. So in terms of the engineering geological properties of siltcretes, how do they differ to ferrocretes?
They're very different. Siltcrete is exceptionally hard, and it is generally got no voids in it at all. It looks, I suppose you could equate it to looking like a piece of quartz or a piece of glass almost in most cases, whereas a ferrocrete tends to be an agglomeration of stuff, and it's really the iron oxides cementing other particles together, and the other particles could be sand or gravel or so on and so forth. And ferrocrete, depending on the degree of cementation, can range from the equivalent of a pretty hard rock down to a very stiff soil in its nature. Siltcrete typically grey white color, ferrocrete typically orange brown color. Yeah, so they're both pedicretes, but very, very opposite ends of the scale, really.
Okay. All right, Mike, having a look at the time, there's no other questions coming through, but I think that's it for today. So Mike, on behalf of all the attendees today, the GeoDiv and myself, thank you for allowing us to share your presentation, and thank you for giving us your time today for this Q&A session as well. It's much appreciated. Thank you so much.
Well, thanks to those attending, and it was a pleasure.
Okay. All right, to all the attendees, thank you for joining us. Again, my apologies for some of the technical issues we've had today. We're looking at fitting in one more evening lecture this year, so please keep a lookout for that. The email coming through will confirm, obviously, dates and the titles for the next lectures. Once again, my apologies for the technical issues with the sound. The recording will be made available on the GeoDiv website and YouTube in the next couple of days. The web link that was sent out to join this event, it did include a GeoDiv and YouTube link. You can just follow those links to find all our lectures for this year and for 2020. Okay, so with that, thank you all for joining in. Thank you, Mike. Thank you, everyone. Have a wonderful evening further. Stay safe, and goodbye for now.